We're going to go over the open book test for Unit 2324 of Calculus. We've learned the product rule, the quotient rule, and the chain rule. And remember, everything that we do involves the order of operations. Got ahead of myself there. So let's review just a little bit. To find the derivative of a sum or difference, the derivative of a sum or difference is the sum or difference in the derivatives. The derivative of a product, you take the first times the derivative of the second plus second times derivative of first. So there's a plus involved, just like your exponential law. When you take the derivative of a quotient, it is the denominator times
the derivative of the numerator,
and then minus the
numerator times the derivative of the denominator over the denominator squared.
good. So denominator times derivative of numerator minus numerator times derivative of denominator over denominator squared. Good. And then the exponential rule is that you take the exponent times the coefficient and then reduce the exponent by 1. And in parentheses, we have what we call the chain rule. So when there's a parenthesis, we begin to see the chain rule, which is to take the derivative of the function and then to take the derivative of the guts of the function, or we would call those guts u. So if we had a situation like this, and there was some exponent, then we would have created a chain. So we would take the derivative of that exponential wrapper, the function, and then times the derivative of what's within that wrapper, which I call the guts of the function, but it's the u, if you want to use u terminology. So if I say guts, don't let it bother you. I see that as I always say that here we have a parenthesis wrapper, is what I say in Algebra 1, and then we would look within that parenthesis wrapper and say, well, what's in there? Well, I've got multiplication in parentheses, so we have the wrapper, kind of like a rib cage, and within that rib cage is the guts within are the what's inside that wrapper, okay? And that's what in calculus we're calling the u. Okay, all right. So we've got a rule for every operation. What we don't have is if we had f of x is equal to x plus y. We don't have that second variable, which we introduced in algebra. We learned about one variable equation solving, and then we threw in just like 2x plus 4 equals 6, and then we went from that to f of x is equal to 2x plus 4, and that gave us a linear equation. But we're going even deeper than that, and we're going to throw a y into the other side and actually try to find the derivative of that later, okay? So we haven't gotten to that yet. Okay, so this is, it's saying to use the product rule. Sometimes we could actually multiply and avoid the product rule and just use the sum or difference rule, but this told us to do it this way, so that's what we're going to do. We're going to follow the directions here and use the product rule. So to find the derivative using the product rule, we would take what? We would have, how did you say it? First times the derivative of the second. Now we usually don't use that radical, right?
Right.
What do we usually do?
X.
Rewrite that as an exponent. So we would rewrite that as the exponent, x to the 1/2, and then cosine x. So written in exponential form, which is a more proper form, we would then have the first x to the 1/2 times the derivative of the second. Now what's the derivative of cosine x?
Negative sine x.
Negative sine x. Now, I'm going to put the negative in front, if that's okay. Negative sine x, am I good at that? And then, what do we have after that? We have first times derivative of second, then
Plus.
plus
Second times the derivative.
second times derivative of first. The second then was cosine x times the derivative of the first. So how do you find the derivative of the first?
Multiply the exponent by the coefficient.
Exponent times coefficient,
Subtracting by the exponent.
and then subtract 1 from the exponent, and that's like 2 over 2, right? So 1/2 minus 2/2 is negative 1/2. Now we'll clean that up with the negative exponents and the fractional exponents, and so now we're going to have f prime of x is equal to negative sine, negative, what's the 1/2 power? Square root. So we're going to put that back like that now. Negative square root x sine x. And then we've got this 1/2 here. So we're going to put the coefficient first, 1/2 cosine x. But then we've got this negative 1/2 power. What does that negative do? It goes to the bottom, and then x to the half is square root x. But see that? The negative, put it on the bottom. What did it put on the bottom? X to the half, which is square root x. Now, that 1/2, since there's a denominator now, we would actually put the 2 in the denominator, right? From the 1/2, and so what we've got is cosine x over 2 square root x. Okay. Now, in calculus, sometimes we just let you stop because it just kind of gets to be a bunch of manipulation. But let me continue on. We're gonna say, okay, we'll be satisfied if you leave it right there. But if we go back to some of the basic rules of algebra, I want us to kind of look at that. What is it that we would not like about that if we were in an algebra class?
Square root.
We don't like that square root on the bottom. So we could just play with this for a long time. We could say, okay, I don't like that, so I could rationalize that denominator if I wanted to. And what that would give me is f prime of x is equal to negative square root x sine x plus, and then that's an x right there. That's square root x. And so then what I would have is square root of x cosine x over 2x. And I can say, well, you know, it's still kind of yucky, but I don't have a radical in the denominator. And then you might say, well, I'm adding, and so it would be nice to get a common denominator, so I could multiply this by 2x over 2x, and that would give me a common denominator. And I could have f prime of x is equal to negative 2x square root x sine x plus square root of x cosine x all over my common denominator now of 2x, so I rationalized it, and now I've added with a common denominator. And you can say, okay, we like that, but if we wanted to factor out, we sometimes say, well, we can leave it in expanded form, because when we start in Algebra 1, we say, well, we want you to distribute. And we get to college algebra and we say, well, we want you to factor out, so which one we're going to call simplest form. So you can see that you can just keep manipulating and manipulating. But again, when we get to this level in calculus, sometimes we say, well, we're just going to leave that radical in the denominator, not worry about it. If we want to deal with that later, we can. We're right now focusing on the derivatives. All right, any questions on number 1? Okay. Number 2, we realize that we could multiply those two binomials and treat it as a sum or difference, but the directions were use the product rule. So we're going to follow the directions and use the product rule. Okay, so the product rule, we would do g prime of x, let me get reoriented here. g prime of x. So what do? To find the derivative, you take the
First
times
times derivative.
3x squared plus 2 times the derivative of the second, which would be
12x squared.
12 x subtract 1 squared minus the derivative of negative 3 is, because it's the derivative, it's the sum or difference, right? So it's the derivative of the difference. What's the derivative of negative 3? 0. So that would be minus the derivative of the difference is the difference in derivatives minus 0, which is gone. That we wanted to talk about that. Don't forget that. It would be minus the derivative of the 3, which would be a 0. Okay, so that's the first part. We have first times derivative of second. Now we have a what?
Plus.
A plus sign. Plus second, which would be the 4x cubed minus 3 times the derivative of the
first.
which would be
6x.
2 times 3 is 6x. Subtract 1 from the exponent. So it would be 6x to the first. And then plus the derivative of 2, which is 0. And that 0 goes out. Okay? So to simplify then, we would need to distribute here and distribute here. And so we have g prime of x is 36x to the 4th plus 12x squared when you distribute there, plus 24.
It'd be 24. 12 times 2.
12 times 2. I missed it. Thank you, sir. Plus 24. There you go. X squared. Plus 24x to the 4th minus 18x. When you multiply with like bases, you add the exponents. Okay. Isn't it interesting? I just want to bring this to your attention again, that there's a lot of things that are built into the order of operations. When you multiply with like bases, you add the exponents. 3 plus 1 is 4. And when you do the derivative of a product, there ends up being a sum in the middle. So the order of operations just keep showing their face in a lot of different ways. Okay, now we're going to combine any like terms, and we've got an x to the 4th term here and an x to the 4th term there, so we can combine those, and we will have g prime of x is equal to 59x to the 4th, 60. That's weird. I was seeing a 5. I was seeing 35 and 24. Wow. Thanks. So we have 60x to the 4th plus 24x squared minus 18x. Let's see how we got that. Now, in Algebra 1, we would have said, okay, that's as far as you go. There's not any like terms. But then later, as we learn how to factor in things, we say, well, we don't want to leave it in non-factored form. We prefer to factor out those common factors. So we could factor out, if we chose to, a common factor of 6x. And that would give us 10x cubed plus 4x minus 3. And this is what we prefer. We prefer, if there's a common factor, that we pull out that common factor. Any questions on number 2? The reason we like to pull that out is in calculus, there's a lot of applications where we would love to find canceling opportunities, right? Factor out and cancel, factor out and cancel. So as we get into college algebra and higher level math, we're always looking to factor out to create some cancellation opportunities. So it's kind of good to be in the habit of that. Any questions on number 2? Alright. Number 3 says, find the derivative using the difference quotient. Find the derivative using the difference quotient. And so, the rule is to do what? To find the derivative, we do what? We take the denominator, which is 3t minus 5, times
The derivative of the numerator.
the derivative of the numerator, which would be
3t squared.
3t squared, denominator times derivative of numerator, and then minus, because division drops to subtraction, okay, in the order of operations. That's a way to remember, but anyway, and then numerator,
Derivative of
numerator t cubed plus 3 times the derivative of the denominator, which would be the constant 3
over denominator squared.
over the denominator 3t minus 5 quantity squared. And as we can, we know that it's good to leave it in factored form so that we might find it.
You'll have to take your 3t minus.
Okay, I got it. Where did it go? Oh, it's in here, because I wiped it out and I put my pencil back and lost my 3. Wow. Thank you. I've been hunting that guy later. Okay, so let's review that again. We have denominator times the derivative of the numerator minus numerator times the derivative of the denominator all over the denominator square. So the denominator appeared 3 times. Okay. So he has that process there. So now we're going to simplify as we can. We can distribute here, and we can distribute here in the numerator. And so we'll have h prime of t is equal to 9t to the third minus 15t squared plus 3 minus, we're going to distribute the negative from this side and distribute 3 from that side, just like we're distributing a negative 3. So that'll give us a minus 3t cubed and a minus 9. All over 3t minus 5 quantity squared. Right, we have some like terms up here that we could combine. So we're going to have h prime of t is equal to 6t cubed minus 15t minus 9 over 3t minus 5 quantity squared.
15t squared.
15t squared. Thank you. Boy, I'm not catching stuff. That'd be dangerous. I'm glad you are backing me up. So, those that are listening, that teaches you be careful with your eyes. Be careful, little eyes, what you see. I don't see. Double check. All right. And then we could look for reducing or cancellation opportunities, and we look at that and say, well, it doesn't appear that we can do some fancy factoring except for that common factor of 3. We can pull that out. H prime of t is equal to, we factor out a 3, and we would have 2t cubed minus 5t squared minus 3 over 3t minus 5 quantity squared. There's no factor in the numerator that would cancel a factor in the denominator. What's in the parentheses, if we could get that to factor out a 3t minus 5, then that could cancel, but that's not going to happen. So that's all of the factoring, canceling, simplifying opportunities that we have. Any questions on number 3? That's about as good as we want to get that one. Okay. So the derivative of a quotient is denominator times derivative of numerator minus numerator times derivative of denominator over denominator squared. Okay. All right. Number 4, we're going to solve using the difference quotient. We're going to solve using the difference quotient. We could pop the t to the 4th to the top and put times t to the negative 4 and use the product rule. I said difference quotient, I meant the quotient rule. I can't be saying this right. The difference quotient is the slope formula. You know that. Okay, the quotient rule. So, let's follow that rule. We're going to have f prime of t is equal to, we're going to take the denominator, t to the 4th, times the derivative of the numerator. What's the derivative of sine t?
Cosine t.
Cosine t. And then when we were dealing with the quotient rule, there's going to be a minus in there, right? Minus the numerator times the
Derivative of the denominator.
which would be
4t to the
4t to the 3rd. I was going to try to draw that, and it's not letting me do. So 4t to the 3rd all over. And I'm just going to write it like this: denominator, denominator t to the 4th squared. Which we know is t to the 8. When you raise an exponent to an exponent, here's the exponential rules again. When you multiply with like basis, you add the exponents, divide, you subtract an exponent on an exponent, you multiply them. 4 times 2 is 8, and so that will become a t to the 8. Okay. Is there any, we've got some factoring opportunity. Obviously, there's a t to the 4th in the first term. There's a t to the 3rd in the second term. So we can factor out a what? A t to the 3rd. So we've got f prime of x is equal to t to the 3rd times a t cosine t minus a 4 sine t. We factored out the t cubed, and that's over t to the 8th. Now that does create, since we factored out, and you see why we keep factored out, this one does create a reduction opportunity. And so we have f prime of x is equal to t to the 3rd with t to the 8th. When you divide with like basis, you subtract the exponents. And so we're going to have t cosine t minus 4 sine t now over t to the 5th. Okay? And that's about all we can simplify. Any questions on number 4? So we've dealt with the derivative of the sum or difference. We dealt with the exponent rule. We dealt with it first, and then the sum or difference. And then we dealt with the derivative of a product, the derivative of a quotient. Now we want to deal with when there's parentheses and it creates a chain. Okay? So the derivative using the chain rule. We can obviously take that binomial 7 minus x cubed and multiply itself 4 times and then distribute a 5 through that big old huge expansion and then use the sum or difference rule. But the chain rule may even be easier than all that. The chain rule is really focused on the parenthesis wrapper, right? We have this wrapper. And what we do is we say, okay, within that wrapper, we're going to call what's in there a single entity, okay? So there's our single entity, which I call the guts of the function. We could think of it as U, and I don't usually write things in U form, but this would be like 5U to the 4th. And so we're focusing on the inside being U, or being a single entity, or as I call it, the guts of the function. Okay? So what we're going to do is we're going to take the derivative of the function times the derivative of the guts of the function, right? So, how would you find the derivative of the function itself? Well, exponent times coefficient. We just return what's in there. We return our U value, our single entity, our guts, and we reduced our exponent by 1, and so we've done the derivative of the function, and then it's times the derivative of the U, the derivative of the single entity, the derivative of the guts of the function. The derivative of 7 is 0. It's a constant. It goes out, so we can focus on the derivative of this second term. So we take exponent times coefficient, which would be negative 3x, and then reduce that exponent inside there by 1, which would be a square. Okay? So the derivative of the function with the single entity placed back inside times the derivative of the single entity, or the derivative of the function times the derivative of the guts of the function. Okay? Any questions so far? Now, we could do some rewriting of that. We could say y prime is equal to, well, if I multiply those numbers, I would have negative 60 x squared times 7 minus x. This is a square right here. That's a cube. That's a cube. Cubed. There we go. Negative 60x squared times 7 minus x cubed. Cubed. Okay. Now, you think, well, we could multiply that cube thing out, but we usually factor instead of expand at this level, right? So then we would just leave it as it is. So we generally leave answers in factored form, not in expanded form. Any questions on number 5, using the chain rule? Okay. When we get to number 6, you think, well, it'd be simple just to distribute that 3, but it didn't allow us that. It said use the chain rule, so we're going to use the chain rule. Okay? So how would you use the chain rule on that? Well, I've got an understood exponent of 1. And what created the chain was the parenthesis wrapper, right? And my U, or my single entity, or the guts of this function, is what's inside the rib cages, what's inside the parenthesis there. So we're going to take the derivative of the wrapper, the function, and then we're going to take the derivative of what's inside that wrapper. So f prime of x would be equal to, well, if we just use the wrapper, then we've got exponent times coefficient 3 times what's inside the wrapper raised to an exponent of 1 less, which is 0. Now, what is that? What's the derivative of x? 1. What is the derivative of x1? Well, the exponent is 1, right? And you're going to multiply exponent times coefficient, and you're going to get 1. And then you subtract 1 from the exponent, and you're going to get an exponent of 0. And what's anything raised to the 0 power? 1. And 1 times 1 is 1. Well, this entity raised to the 0 power is 1. And 3 times 1 is 3. So, if you thought of this big old thing as being a big O X or a big O U, then it would be like taking the derivative of 3u, which is 3, or the derivative of 3x, which is 3. So, the derivative of 3 times single entity is 3, just like 3x is 3. Okay, so we got that. I wrote that out. We'll try to clean up just a little bit. So, let's continue. I'm going to leave it written like that. And then we'll change it again just so we can say it again. So we had, let me start. We have, this is to the first, so we have 3 times the derivative of single entity to the first power. The derivative of anything to the first power is 1, and so we really have 3 times 1 is 3. So when we take the derivative of the function, we get a 3, and now we want times the derivative of the gut to the function. And we have a sum, our difference. The derivative of the first part is 2x minus the derivative of the second part is 6 plus the derivative of the third part is 0, so it goes out. Let's see what we got to there. And so then we can distribute or leave it expanded, right? If we were to distribute, then we could factor that 3 back out. Sometimes when there's not multiple terms, then we will distribute and get 6x minus 18. If there were multiple terms, we might want to write it in factored form. So because sometimes we do, sometimes we don't, then, we can kind of take it either way on that. As we get something down to early algebra 1 level, we tend to want to go ahead and distribute. But when it's getting into higher ordered exponents, we begin to think, well, let's leave it in factored form. So some of that's going to be sufficient either way. Any questions on 1 through 6? Well, the next part says find the derivative using the method of your choice. And the reason is here was we realize that it's not always the easiest thing to do the quotient rule or the product rule. And if we had some factoring or some canceling opportunities, we might could write it in a much simpler form. And so we'll take the opportunity to do some of that. Now, first of all, we're just going to take the derivative of tangent, and that's a memory work thing, just to toggle your mind a little bit on the derivative of sine, cosine, tangent. Let's write all those down again, just so we can see if they're in our memory. What is the derivative of sine x? If we had y equal sine x, then y prime would be cosine x. If we had y is equal to cosine x, then the derivative would be negative sine of x. If we have y is equal to the tangent of x, then the derivative is secant squared x. Excellent. If we had y is equal to cosecant x, then the derivative of cosecant x is
cosecant x times cotangent.
good. And if we had y equal secant x, then y prime would be,
Secant x times tangent x.
so we have y equal secant x times tangent x. And if we had y equal cotangent x, then the derivative is
Right, negative cosecant squared.
negative cosecant squared x. Good. So those are our derivatives of the trigonometric functions. Excellent. So when we look at y equal tangent of x, y equal tangent of x, then the derivative there is secant square x. And we saw some familiarities there. We saw that tangent was connected to secant, and when you come back here to the derivative of secant, we have tangent involved again. We saw that cotangent was connected to cosecant. And when you look at cosecant, we see that cotangent is involved again. We notice that the tangent and cotangent are the ones that have the squares connected. I just walked out my square. And we also notice that anytime it has a C, there's a negative. C, negative, C, negative. Okay? So every time there's a C in the original function, there's a negative in the derivative. We see that tangent is connected to secant. When you have tangent, there's going to be a square. Cotangent is connected to cosecant. The C's are connected to the C's. Okay? The C's are connected to the C's. And the C's are connected to negatives. Okay, you understand all that? That's a good way to learn that. Okay, I probably shouldn't have messed all that where you can't see it. Any questions on number 7? Okay, number 8. Number 8, we could use the product rule, or we could multiply the binomials, right? If we were to distribute, we could send the 8 through, and then we could send the 2 through. And we were just rewriting the form of g of x. We're not taking the derivative yet. So we would have 24. 8x times 3x is 24x squared. And then 8x times 4 is 32x. And then 2 times 3x is 6x. And 2 times 4 is 8. And then we could gather like terms, combine like terms. We get g of x is 24x squared plus 38x plus 8. So we rewrote the original function as a sum or difference. And now we're going to use the sum or difference rule rather than the product rule. If we're used to the product rule, you may think, well, I could have done it with the product rule as fast as having gone through all that, which is very likely the case. At this point, if we do the derivative, we have g prime of x is, we know that the derivative of a sum or difference is the sum or difference of derivatives. So we would have 2 times exponent times coefficient. That would sound good on the air. So 2 times 24 is 48. X, reduce the exponent by 1, which is x. And then we know the derivative of 38x is the 38, and the derivative of the constant goes out. So g prime of x is 48x plus 38. Okay. Any questions on that one? All right. Well, we've got several left. We'll just stop there, and we'll have another recording for the last part. Appreciate your attention.